En nu eerst de sterren. Want met grote blijdschap delen wij u mede: A Star is Born.
This incredible pool of molten rock is on the flanks of the active volcano Kilauea on the island of Hawaii.
It's only when you're standing close to a seething, teeming lava lake like this that you're forcibly reminded 5 billion years after the Earth was born, parts of it are still hot and active. Truly, our planet was born of fire. It's almost impossible to conceive the forces that must have been around to make it come into being. And yet our Earth, and you and me and all the teeming life it now supports, are just byproducts of a much more tremendous act of creation, the birth of our local star, the sun. Our sun was born so long ago we might never know how it happened, but other stars are being born now. And astronomers are studying these new stars, not just to answer the questions as to how and why stars come into being, but why there's all this activity, and why, in the end, there's life itself.
Star birth is as old as the universe. It has been going on for 15 billion years. The universe contains 100 billion galaxies, each a vast, rotating star city. We can look sideways across our own galaxy, the Milky Way, and see that it contains 200 billion stars, including our own sun. At 5 billion years old, our local star is a relative newcomer to the scene. And there are some places in the Milky Way, like the Orion constellation, that are active regions of star formation. Even in the past, people regarded Orion as special. Our ancestors could see the shape of one of their favorite heroes in the stars, an arrogant hunter wielding a sword and a club, who boasted that he could kill every animal on Earth. Mythology apart, there's something even more special about Orion and about the middle star in his sword in particular. It isn't really a star at all. Instead, it's a huge cloud of glowing gas called a nebula. Deep inside this nebula, actual star birth is taking place now. The trouble is you can't see it for dust, literally. This gas and dust cloud is so dense, we can't see what's going on inside.
But now astronomers can see things in a new light, infrared heat radiation, which is how you're seeing me now filmed through a special infrared camera. It's incredibly sensitive, and you can see immediately that my face is fairly warm, but my poor nose has got very cold. Let's see how my hands are getting on. As you see, the palms are quite warm, but the fingers haven't yet caught up. You're seeing me through an infrared camera, and that's alongside our standard television camera. And this is just to prove I still exist. Newborn stars emit lots of infrared or heat radiation as well, so you can use a special camera like this to pick them up. But the great advantage of infrared is that it penetrates dust or smoke or any obscuring material, so it's as if it wasn't there at all. And just to prove this, cue the smoke generator. And as the smoke slowly comes up to cover me up and I disappear from view, you can still see my infrared signal loud and clear. And that's why astronomers really appreciate infrared, because it allows them to probe the hidden secrets of star birth.
Just what is really going on inside these dust clouds is being revealed for the first time by a new generation of infrared telescopes, one of them built to fly in space. To get the best infrared views, scientists put together a special space telescope, IRAS, the Infrared Astronomical Satellite. IRAS was planned to last just 1 year before running out of the refrigerant that kept its detectors cold enough to sense the infrared sources of deep space. It was a great success and discovered many new sources of heat from hot young stars.
We detected infrared emission from 250,000 discrete sources, made images of the entire sky, and made discoveries on all scales within the solar system, within our galaxy, and in of external galaxies beyond. And some of the most important ones, I feel, are in the area of star formation, where we found stars very much like our sun must have been 4 billion years ago, in the process of formation out of clouds of gas and dust. IRAS revealed a totally new picture of Orion. One sees a giant gas cloud that extends over 30 degrees of the sky, and throughout the region, giant stars, thousands, tens of thousands of times brighter than the sun, are forming out of these pockets of gas throughout the molecular cloud. In turn, these giant stars disrupt the cloud, and over thousands of years, new stars are revealed to the naked eye. Much of what you see here is totally invisible to the naked eye, taking place only at infrared wavelengths.
An even more spectacular IRAS discovery was the new view it gave us of heat sources from hidden stars within our own galaxy, the Milky Way.
One can see very little of the Milky Way from optical telescopes simply because the gas and dust obscure our view of it. One only sees maybe a few thousand light years. The center of the galaxy is over 24,000 light years away. With IRAS, we see the star formation regions throughout the galaxy, and there are literally thousands of them.
Its refrigerant exhausted, IRAS now floats endlessly and irretrievably in space. But its results are still being analyzed, amongst them a starbirth map of the heavens.
Take me into space, but it'll take me to the next best place, the world's highest observatory. I'm on my way to the 14,000-foot summit of Mauna Kea, which, believe it or not, is on Hawaii. You're above most of the water vapor at 14,000 feet, which absorbs infrared radiation. And on the summit of this mountain, astronomers from many countries have come together to build the world's highest sighted and fastest growing collection of telescopes.
At this altitude, you have to cope with lack of oxygen, usually with freezing temperatures, and sometimes with 100-mile-an-hour winds. So why do astronomers come all the way up here to investigate starbirth?
Well, it's a great place because most of the astronomy is infrared, millimeter or sub-millimeter astronomy, which requires a lack of water vapor. The water vapor in the atmosphere absorbs everything that we're trying to detect. So by being up here at 14,000 feet, we're above 90% of the atmosphere. We're looking at stars before they're stars. Instead of looking at bright pinpoints of light, we're looking at dark clouds of gas, which are collapsing at room temperature, and somewhere inside there's a star being made.
The air on Mauna Kea may be thin, but it's chock full of atoms compared to the vacuum of space. Except that space itself isn't a vacuum. Well, not quite. Imagine I could take a scoopful of space stuff with my hands. It would contain just about 4 or 5 atoms, which is absolutely nothing compared to the billions of atoms I'm holding here, even 14,000 feet above sea level. But those thinly spread atoms in space are vitally important to us, because those rarefied atoms are the stuff of the next generation of stars.
Star stuff is spread incredibly thinly through space, but it has all the time in the universe on its side. Over millions of years, the tendrils of gas begin to build and collect into something substantial, like the coal sack, a black patch in the Milky Way. Silhouetted against the distant stars, these clouds are black and impenetrable due to tiny grains of sooty dust that are swept up with the gas as it starts to accumulate. As these gas and dust clouds start to grow, the atoms inside begin to stick together in groups of 3 or 4 or even more. These are molecules, the first step in the process of star formation, a process that may also lead to the birth of planets and life.
But how how do we know all this? Well, the telescope behind me, here on the summit of Mauna Kea at 14,000 feet, is one of the only ones in the world to look inside these gas and dust clouds to see what's going on. It's Britain's James Clerk Maxwell Telescope, or JCMT, and what it can do is to tune into signals from the twisting and tumbling groups of molecules deep inside these clouds long before starbirth proper begins to take place. The JCMT is a revolutionary new telescope. It's exploring a window on the sky that's never been studied before by looking at radiation from space that's halfway between infrared radiation and radio waves. You can use the JCMT right around the clock, even during the day, because it's not blinded by light. But as wind or strong sunlight could so easily warp its 50-foot aluminium dish, you always have to observe with a protective shield up. It's made of a special fabric, a bit like sailcloth, that still lets the radiation through onto the dish. And the JCMT is capable of detecting the very earliest moments of starbirth. It has produced this density map of a very cold dust cloud. The white region reveals that in the middle, particles and molecules are starting to attract each other and condense under the forces of gravity. This image shows us the exact moment of conception of a new group of stars. At this stage, the temperatures are still very low, but as the simulation shows, gravity slowly but surely begins to bite. Gentle swirling turns to unstoppable collapse. This is the point of no return. But what happens next? To find out, it helps to have direct pictures. And just across the summit from the JCMT is another British telescope which can do just that. It's UCIRT, the UK Infrared Telescope. UCIRT follows the collapsing gases inside a dust cloud as they begin to get hotter under compression. But at what point do those collapsing gases actually become a star? And has anyone seen a star being born? Not so very long ago, early one morning, a team of astronomers using this telescope got to see starbirth in action for the very first time. The leader of that team was Ian McLean.
On the morning of October 23rd, 1986, we came to the UK Infrared Telescope to use a new infrared camera using a state-of-the-art television device capable of detecting heat radiation from distant sources in the universe. What we're looking for is the heat emitted by young sources, young stars, embedded in gas and dust. We know very little about the star formation process. We understand that stars form out of the cool gas and dust in the interstellar medium, but we don't know whether stars form singly or in pairs, and we don't know how planets form around stars. And without knowing how planets form, we can't really say very much about the occurrence of life in the universe. Now, our first job was to get IRCAM, the infrared camera, ready for operation. First of all, we filled it with liquid nitrogen to cool the detector to 35 degrees above absolute zero. Okay, Dolores, can we slew to the trapezium now, please?
Okay. Then they tested the new camera by pointing their telescope towards a group of stars in the Orion Nebula. It was already 8 a.m. and the sun had risen, but the infrared camera IRCAM, like the JCMT, can see the stars even during the daytime.
Okay, we're there.
Although this was their first attempt using their new equipment, they were immediately rewarded with a discovery. For the very first time, they could see a cluster of newborn stars, the large red area on the right, hidden deep inside the nebula.
This is an important discovery. It is important because the tool that we have used for the first time allows us to see deeply into star-forming regions, to see faint sources as well as bright sources, and to probe the whole spectrum of masses of forming stars.
Now astronomers can begin to piece together the story of how a star is born. First, the gas cloud starts to collapse and condense into a number of cores. Each core, now collapsing on its own, is destined to become a new star. The UK infrared telescope shows these young protostars, which grow hotter and hotter as they shrink. And, one by one, each becomes so hot that its nuclear fires are ignited, the moment of birth. The fragment is then no longer a part of a collapsing gas cloud. It is a stable star, generating its own energy. But around the young star, all is chaos. Eventually, the young star shoots powerful beams out of its poles, driving away the leftover debris. Now the construction site begins to clear. At this stage, the young stars are still surrounded by the remains of the gas cloud. This gas is lit up to form a glowing nebula, like the Trifid Nebula, a nursery for young stars. Nebulae, while they last, are undoubtedly the most beautiful and most photogenic byproducts of star birth. But a nebula's days are numbered. Violent winds blowing off the young stars will eventually drive the nebula away into space, maybe to make stars in another part of the galaxy. These breathtaking pictures were taken by David Malin. He doesn't use infrared or false color, just ordinary film. But he has an extraordinary camera, the huge Anglo-Australian telescope in New South Wales.
Many astronomers don't believe they can do real astronomy unless they're pounding away into a keyboard, unless they're talking to a computer. Older astronomers, of course, have had experience with photography and have appreciated what kind of information you can derive from it. I guess I'm one of the older generation, although I still think of myself as quite young, and prefer to use photographic techniques to extract the information that I want. The work at the telescope is the essence of obtaining the data, come back to base with the processed negatives, and then the work of extracting the data from them begins. At base, the plates are often, in fact, the plates are always copied to some form or other. It depends what I'm going to do with them. If I'm looking for very faint objects, I use a photographic amplification process to find very faint things, or I'll play around with unsharp masking techniques to fish out other kinds of information from the plates, or I might make them into a three-color picture.
And that's the technique that he uses to capture the Horsehead Nebula, a dark cloud poised to form into stars.
As soon as stars begin to settle down to a steady-state burning, they emit quite intense stellar winds and begin to blow away their natal material, if you like. The afterbirth is blown away by intense stellar winds from these stars. And as the scene clears, you begin to see the stars as individuals, often hot, young, blue stars, with nebulosity blowing away from, streaming away from them, as it does, for instance, in the Orion Nebula.
David Malin's long exposure photos have shown us for the first time what deep space really looks like. They don't just show stars. They bring out all the subtle textures of dark dust clouds and nebulae lit up by newborn stars inside. While David Malin probes the immediate aftermath of star birth, other astronomers are using the UK Schmidt telescope, also based in Australia, to investigate the later, less glamorous stages of star formation. They're following the inevitable breakup of a star family, how the nest of active young stars born in a gas cloud moves apart as they begin to follow their own paths through space. What they're trying to resolve is why gravity often holds some of the stars together. Among the millions of stars on this plate, they've found many that have stuck together from birth as pairs of stars, double stars. In fact, single stars are surprisingly in the minority. More than half of all stars in the sky are double. There are some double stars in the sky you can pick out with no trouble at all. A lot of people know the stars Mizar and Alcor in the Plough. In fact, the North American Indians call them the Horse and Rider. Even more spectacular is Epsilon Lyrae. To the eye alone, it's a double star. But through a telescope, you discover that each star is again double, making it a double star. But there is one star we know is single. If most stars are double, why isn't the Sun? The answer is that it was born with some companionship. Not the companionship of a massive star, but of several far smaller planets like our Earth. After the Sun was born, a great deal of material was left over. Most of it settled into a disk around the young Sun, a swirling jumble of matter, sometimes colliding and breaking up, sometimes sticking together. The first signs of young planets. Clumps of rubble and debris began to grow, steadily attracting more material as they grew bigger. Close into the Sun, it was too hot and chaotic to make much headway. Only small, dense worlds, like the Earth, were able to form. But further out, where it was cooler and less violent, the larger planets like Jupiter and Saturn were able to grow. But how common are planets around other stars? Is our solar system a freak, or do planets form naturally as a byproduct of starbirth? Only now are we beginning to find some clues.
One of the most spectacular discoveries that took place during the course of the IRAS mission was the fact that many nearby normal stars have a very large infrared excess. And this excess can be attributed to dusty material orbiting around the star, heated by the star enough to glow in the infrared. A spectacular confirmation of this result and an extension in our understanding came when two American astronomers, Rich Terrell and Brad Smith, took an optical photograph of one of these stars, Beta Pictoris, and found an edge-on disk of dusty material. And it's the combination of the IRAS results and the optical photographs that really lead people to the idea that many stars are surrounded by these dust lanes, these edge-on disks of material, and it's the analogy to our own solar system that leads people to think that these disks are really the stuff out of which planets might someday form.
We know there are 200 billion stars in our galaxy. We don't know if they have planets orbiting around them, but if planets are a natural byproduct of starbirth, then there could be billions of planets in our galaxy alone. If that is the case, the implications for all of us, not just for astronomers, are vast. And the reason is because only planets can support life.
The whole question of life on planets other than our own is a very difficult and challenging one for astronomers, philosophers, indeed for everybody. And one has to ask the question, break the question down into a number of different areas. Are there planets around other stars? Are these planets at an appropriate distance away from the star to be warm enough but not too hot for life to form? And so on. And the first of these questions, the existence of planets around other stars, is now coming into our technological grasp so that we will be able to answer it scientifically in, I would say, the next 10 to 20 years. And we'll get away from having answers that are really religious in nature, yes, I believe there are other planets, or no, I don't, and really get to a scientific answer to the question, is it likely that there's life elsewhere in the universe?
To be able to detect an Earth circling another star would be an incredible achievement and somehow reassuring, because it would mean that the Earth wasn't just a one-off, that it wasn't unique in the universe. But that wouldn't be enough for us. We'd soon be asking, is there life on that other Earth? And from hundreds of light years away, would we ever be able to tell? Well, one day there may be a way, because life has fundamentally altered this planet from the way it used to be. The early atmosphere of the Earth consisted of noxious gases belched out of volcanoes like this one. But when plants got a foothold, everything began to change. Plants breathed in carbon dioxide gas and gave out a very rare gas in return, oxygen. Oxygen's virtually absent from any of the other planets, but for us, it's our cornerstone. Because without oxygen, none of the higher life forms would be able to exist.
The next generation of infrared telescopes in space will not just look at the birth of stars and planets. They will scan the skies for the evidence of oxygen on other Earths. And so they may one day reveal whether the birth of life itself is as commonplace as the birth of stars, whether we are but one of many inhabited worlds, or utterly alone in space.